Welcome to this introductory lecture on network latency. My name is Anna Brunström and I'm professor in computer networking at Karlstad University. In this lecture we will look at network latency and why it is important for application performance and how it relates to other performance measures such as data rate. Historically, there's been a very strong focus on optimizing throughput and link utilization within the networking community. Early on, this was a natural choice because the link capacities available were very limited, and then increasing the capacity and using this capacity fully really helped application performance. But as the network capacities has increased, this is no longer the main limitation on application performance in many cases. Instead, latency is really a key performance limitation. There is also confusion thinking that the data rate, or as it's often referred to, bandwidth, is equal to the speed that we will perceive for our application. So when we talk about network connections and we, for instance, advertise them, we very often say that you have a high-speed connection if you have a high data rate for your connection. But of course, the high data rate may not mean that your application is perceived as very rapid and responsive. So data rate is really about how many bits you can transfer per second, but the speed that you perceive as a user is really how long it takes to complete a task. And today, as I mentioned, the users often does not need higher data rates to have a feeling of speed, but they need less delay. And this means that today reducing latency is a key enabler for end user experience, and it's also a key enabler for new services. So where does latency matter? Let us look at a few examples. So if you are used to playing games, then you are probably also experienced with network latency. When you try to interact with another user online in the game and you try to perform your actions, then the network latency is really the limitation of how rapid you feel that the game responds. Another example is web browsing. When we surf the web, what limits our performance is often the latency rather than the data rate. There's also been user studies by both Microsoft and Google showing that if you increase the latency in the web communication, this has a direct impact also on the revenue, for instance, from the advertising that you receive. Of course, also all types of interactive media applications are very dependent on latency. So if you perform a voice or video call and you have a latency that is too large, you will feel an unnatural delay in the communication. Latency is a key performance enabler for many of the current applications, but it's also very important if we're looking forward and looking to some of the applications that we are envisioning coming. And an example of that is to look at the emerging 5G use cases. So here one of the key use case areas is the ultra-reliable and low latency communication. And this ultra-reliable and low latency is supposed to enable services such as self-driving cars, machine-to-machine communication for industry automation, or various mission-critical applications such as applications within e-health. And of course, none of these applications are possible unless we have a low network latency. So let us continue and take a closer look at the relationship between the type of application and the relative importance of the data rate and the latency on application performance. So what you see here is an analysis of the startup latency when you start up a reliable communication flow using the TCP protocol. We are ignoring here any type of handshakes and just looking at the so-called slow start phase that you go through at the beginning of a TCP connection in order to probe for the available bandwidth that you can use for the communication. So what we see in the graph is on the x-axis you have the size of the flow that we are looking at, and then on the y-axis you have the average rate that this flow can achieve in the communication. So if we, for instance, look at the flow here of 1,000 bytes, you can see that it would get approximately 0.1 megabit per second as an average rate. And in the graph we have three different lines, and they represent different capacities on the links that the communication is going through. So in the gray dotted line we have 2 megabit per second, in the blue line 80 megabit per second, and the green line represents 1 gigabit per second link. And what you can see in the graph is that you have to have a flow of a particular size before you actually get any gain from increasing the capacity. So to get the gain by going from 2 megabit to 80 megabit, you need a flow size of somewhere around 5,000 bytes. As the capacity is increased, you can see that you require increasingly large flows. So to actually gain something from increasing the capacity from 80 megabit per second to 1 gigabit per second, you need a flow of almost 1,000,000 bytes or 1 megabyte. So you need quite considerable flow sizes to actually take advantage of increased data rates. And if you combine this knowledge with the knowledge that most flows on the internet are actually quite short, then you can see that as data rates increase, we have a diminishing return in terms of application performance for most flows on the internet. And what actually determines their performance is not the available data rate, but rather the latency they experience when they try to take advantage of this data rate and set up their communications. So to look at another example that illustrates a similar point, let's look at some measurements from the mobile networks that we have been taking and some associated analysis. So what you see in these graphs is the relative impact of throughput and round-trip time on the completion time of short flows. So what we have in this graph is on the x-axis again varying flow sizes, and this time on the y-axis we look at the difference in completion time that you would obtain if you increase or decrease the round-trip times or the throughput that the flow can obtain. So the 0 line here, that represents the actual measurements that we have taken in the 4G network in the bottom half and in the 3.5G network in the upper half. And then we look at in the dashed line what happens when you could increase the throughput or decrease the throughput by 10%. And in the solid lines we look at the same change, but this time in the round-trip times. And what you can observe in the graphs is that when you have a short flow, the impact of actually decreasing the round-trip time and the gain you can get from that is much larger than having a similar 10% increase in the throughput. So we see that as the flow sizes, this relationship changes. And if we continued here to even larger flow sizes, we would see at some point the available throughput is actually the determining factor on application performance. But for the short flows, the round-trip times has a much bigger impact, as you can see through the solid lines here. We also see in this graph, if we compare the 3.5G network with the 4G network, that as the speeds increase, this effect gets stronger. And this is directly related to what we just looked at on the previous slide, that as the throughputs go up, you have less gain for the short flows, and you need larger flow sizes to take advantage of this extra available throughput or extra available capacity. So in the 4G network, you see that the round-trip times are having a much larger impact for the short flows than any changes in throughput, which basically have a negligible impact here. So again, for short flows, the round-trip times and the delays in the network are more important than the data rates. So we have seen that latency is critical to application performance. So what is happening if we look over time? Is latency really reducing? This is something that we have taken a look at in some of our previous work. And this analysis is based on a data set from the measurement lab, specifically captured by a tool called the Network Diagnostic Tool. And this tool measures the throughput that the flow can obtain, performing a relatively large transfer, and it also measures the round-trip times that is observed throughout this transfer. So if we take a look at the evolution over time, first looking at how the average throughput has evolved, we see that comparing the graph for 2015 to the graph from 2010 and the graphs in between, there is a steady increase in the throughput that the flows can obtain. So we see higher data rates available, higher capacities. If we then look at the corresponding figures related to latency, starting by looking at the minimum RTT observed during the flow, we see that we have some small reductions here with time, but the difference is not at all as noticeable as the change in throughput. Having a look at the RTT span, the difference between the minimum and the maximum RTTs observed, we see that here we see no improvement over time, and we even have a small increase almost in the RTT span in the later years analyzed. So what we can conclude from this is that while the throughput and the data rates are going up steadily, this does not necessarily mean that you see a reduction in the delays. So of course the increased data rates can also have a benefit for latency, because you can send your data, transmit the data faster, and you can also clear out any queues that have formed at the larger pace, but there is no direct connection. So you may increase your data rates and your latency in a communication path may still go up because you encounter other delay sources or other changes in the communication. So this means that we have to work very carefully to reduce the different sources of delay. So to summarize, we have seen in this lecture that latency is today critical to application performance for many applications. And of course, the relative importance of the data rate and the latency on application performance depends on the characteristics of the application. So when you have very large amount of data to transfer, then the data rate is the key enabler for application performance. But for many applications, when you have shorter flows, you have short bursts, you have interaction between the communicating entities, then the latency is the key dominant factor for the performance that you perceive as a user. We have also seen that while the data rates are steadily increasing, this does not necessarily mean that you also see a reduction in latency. So it's very important to work towards reducing latency, identifying the different latency bottlenecks, and removing them from the network. And we will look closer at some of these aspects later on in the lectures.